Hey everyone, Mr. Dressel here. Wanted to help you out with today's do now if you're still confused after looking at the key. Let's look at this first problem. It's asking us to multiply these three terms right here into these two terms right here. Now, every time you multiply one group of terms into another group of terms, you always have to distribute. And anytime you're distributing more than two members of a group, like for instance, when you have 3 right here multiplied into 2, then using this area model is really nice. One thing is it helps you organize things, put one group along the top, one group along the side, and everywhere they intersect, you just find the product. Like for instance, right here, x squared times 2x, that's 2x cubed. Filling in all of these boxes, the only thing you have to do afterwards is just look for any like terms. And one thing that's really nice is that your like terms oftentimes will just line up diagonally. For instance, there's 12x squareds and negative 3x squareds. Combine that together, you get 9x squared. Same thing, 4x plus negative 18x gives you negative 14x. And then there's only the negative 6 constant, and then there's only the 2x cubes gives us our last two terms. Okay, looking at this second problem, it's asking us to factor. You can see we're using the standard X chart here where you put A times C in the top. That's negative 16 times 1. The B term, the middle term, the linear term, that goes in the bottom. And then we play this game of what adds to the bottom that also multiplies to the top. You can see that we got 8 and negative 2. Now, when there's nothing in front of x squared, these two terms can go directly into parentheses and you can have your factored form. But it's helpful to see this box method as well. It kind of gives an idea of what we're even doing in the first place. Now, anytime you're factoring, you're doing the opposite of what we did in this first problem. You're doing the opposite of distribution. So essentially, if you imagine filling in the boxes inside with information and then using that information to go backwards, that's what we're doing right here. We know that the x squared would be in the first box. If that had a number in front of it, that would still go up here. We know the negative 16 would go in the last box. That's always the constant. And then the two numbers we figured out here, they would go into these side boxes. Essentially, those two numbers represent, once we multiply out, we're always going to get two linear terms, two numbers multiplied by x. Those always combine together to make your b term. So anyway, that's our factored problem right here. Looking next at this third problem, there are many ways that we can solve a quadratic equation. Factoring sometimes, or using the quadratic formula, or one of my personal favorites is graphing when that's available. But in a case like this, where you don't have a linear term, there's no b term in the middle, this is one of the easiest because then you can just solve algebraically. In this case, I could add the 20 to the other side, take the square root on both sides, and I would get x is equal to the square root of 20. The only final step there is that I have to take the square root of 20 and get it into the simplest radical form. So if I do the prime factorization of 20, I can see that 20 is the same number as 2 times 2 times 5. If I have a pair of factors of 2, I can take those out and put them up front. And because I took the square root of both sides, I want to remember to put this plus or minus sign, showing that there can be a positive and negative answer for this. So, one more question. This is asking us to describe how the graph of y equals x squared can be transformed to the graph of y equals x minus 2 squared minus 10. So you can see right here that the answer is that this would move the graph x squared right 2 units and down 10 units. Just to explore this a little bit further, I want to actually look at this graph really quick. So this is the graph of x squared. And I wrote on the site here, here's x squared, and then this is like the transformation, x plus something in the parentheses squared, and then plus k on the outside. Now I can move these and add positive numbers, and you can see as I add positive numbers, it moves the graph to the left. And as I add negative numbers, this is adding to the x inside, you can see that that moves it to the right. So the way I kind of think about this, if you think of the x-axis as time, and it's not always time, but in a lot of real-world situations it is, I think about adding a number. Adding a number to the x-axis is kind of like saying that this whole function happens, but everything happens too early. And that if I'm subtracting a number, it's like all of the same things happen, but everything happens exactly too late. It happens 2 maybe seconds or 2 minutes later than it would have originally happened. Then adding and subtracting outside of the parenthesis, I think makes a little more sense, because that's just like if I originally had an answer of 0, once I add something on the outside, maybe if I add 2, then that just moves that answer up, and it moves every value of the function up. So when I had a value at, at x equals 2, if I have a value of 4, then after the transformation of plus 2 on the outside, that would push it up to a value of 6. That'd be true for every point along this graph. Anyway, I hope that helps you guys out, and have a great rest of your day.